Hello class, welcome to this lesson on 2-5. We're going to be talking about assessing regression models. So our essential question is, how do we determine whether a regression model is appropriate when we use it, and how do we determine how well our regression model makes predictions? So our learning goals are to be able to use residual plots to determine whether a regression model is appropriate, interpreting the standard deviation in the residuals, and interpreting the R-squared value. So we need to know what a residual plot is, what standard deviation of residuals are, and the coefficient of determination. So last lesson we computed the equation of the least squares regression line and used it to make predictions. So now we want to determine how well the line fits the data, aside from just looking at the correlation coefficient R. So the questions that need to be answered are, is a line the right model to use, or would a curve be better? If a line is the right model, how well does it make predictions? So in order to do that, we use what are called residual plots. So remember that a residual is the difference in the actual and predicted values, or the error, in our prediction. So we can use residuals to make this residual plot. So once we make the residuals, or once we calculate all the residuals, we can put it in this scatter plot that plots the residuals on the vertical axis and the explanatory variable on the x-axis, or the horizontal axis. So this is kind of how an example of, a residual plot on the right side. So this right here is our residual plot on the right side. And notice that on the residual plot you have your zero line, right? So this is our zero line, which means that this is where we have perfect predictions, where there's no zero residuals. So if a dot is located on the zero line, that means we made a perfect prediction. If a dot is located above the zero line, that means that it is a positive residual, which means that we, in that case, if it's a positive residual, that means that we underestimated. If it's a negative residual, that means we overestimated. So in this case, so positive residual. All right, so if it's positive, we underestimated. If it's negative, we overestimated. And depending how far away the dots are from the zero line, that tells us the magnitude of that residual, how far away, how big that error is. So ideally, we want those errors to be as small as possible. And we want to look to see if there are any patterns. So if you look on the left side, we have the regression line here, right? And clearly looking at the regression line, that does not seem to be a good model for the data. The model for the data seems to be, a curved relationship, right? So definitely not a linear relationship. However, if you look at the residual plots, this is evident in the pattern. So there seems to be a clear pattern of residuals here. And that clear pattern tells you that the linear model is not an appropriate model for this scenario. If there is a pattern in the residuals, meaning that you consistently overestimated, or you consistently underestimated, this means that there's something wrong with the model. Now, if you're looking at a residual plot in which the dots are randomly scattered but very close to the zero line, that tells you that that model is a good model. So clearly looking at this, the model is not appropriate. If you look at the numbers before Super Bowl 11, we consistently overestimated, or looking at over here, we consistently underestimated, So here, before Super Bowl, we underestimated. So here we underestimated. And if you're looking at between Super Bowl 11 and Super Bowl 33, we consistently overestimated, right? So there's definitely a consistency there. So that means it's not, our linear regression is not an appropriate model for this scenario. And this data represents, Super Bowl, the cost of a Super Bowl, based on the Super Bowl number. So now let's look at another example of a residual plot. So this one are data for Ford F-150s based off of the price of the Ford F-150 based off of miles driven. So if you look on the left side, you have our regression model here. It looks like a very good model. It closely fits the data. And if you look at the residual plot, well, this is the zero line, right? So if you look at the dots, they're randomly scattered above and below. There doesn't seem to be any pattern in the, in any particular dot going up or down. So since there's a random scattering around the residual line, and if you notice that these residuals are quite small, like this residual is about 9. The highest residual that here is, like -8 or +9. So very small residuals. If you compare it to the previous one, the residuals are actually quite large. So here, this residual is 600. Down here, this residual is at -600. So very large residuals. This one over here is 1,000. So the residuals are quite large in this one. So definitely that adds to the fact that it's not a good model. And then if you look at this one, very, very small residuals and scattering in the randomness about the zero line. So this is a good model. This indicates that the line is an appropriate model. All right, so now interpreting the residual plot. So to determine whether a regression model is appropriate, as we mentioned before, you want to look at these following things. You want to see if there is a pattern in the residual plot. If there is no pattern in the residual plot, the regression model is appropriate. If there is a pattern, then the regression model is not appropriate. So also note that residuals should be ideally as close to the zero line as possible, and this indicates that the errors are quite small. All right, so let's look at the following problem. In the previous lesson, we used this least squares regression line to model the relationship between amount of soda remaining and the tapping time for cans of vigorously shaken soda. Here is the residual plot for the model. Use the residual plot to determine whether the regression line or the regression model is appropriate. So in that last lesson, we were able to, come up with a regression model, regression equation. We were able to calculate the correlation coefficient R, all that stuff. Now we're focusing on the residuals. So if you look at the residuals, all right, so looking at the residual plot. So if we have the residual plot that is given here, well, notice that we want to determine if there's a pattern, in the scatter plots. So now let's look at the zero tapping time. For zero tapping time, we have some dots below, we have some dots above. And those are, this could be easily random. So like some dots, there could be more dots below, there could be more dots above. But there seems to be, by chance, there seem to be 2 below and seem to be 4 above. Nothing to be worried about here. Now for this, we have some dots. We have some cans that were at a time of 4, for a tapping time of 4 seconds that were below, and some that were above. Again, nothing, crazy there. We have some that are above, some are below. So this is by chance, that we were above or below. Same deal here. We had some below, some above. So this is by chance that this happens. Some below, some above. So this seems to be, random in the sense that some cans could just as easily be above the line as well as below the line. So if something can occur by chance, or if it's randomly scattered, like it is here, some above, some below, and there's no clear pattern, in that case, we can say that this regression model is appropriate. Okay, so in this case, there is not a clear pattern in the residuals. Which indicates that the linear regression model is appropriate. All right, so now let's talk about the standard deviation of the residuals. So we can measure how well the line makes predictions using the standard deviation of the residuals. So we remember that standard deviation is a measure of the spread. So in this case, the standard deviation of the residuals is measuring, the spread in the residuals. So essentially it's saying what is the size of a typical residual based off of that spread pattern. So S measures the typical distance between the actual y values and the predicted y values, basically measuring the typical residual. So to calculate this, we gotta square each of the residuals, add them up, and then divide by n minus 2. Then finally take the square root. So this formula is given below. Remember that this sigma means sum. This right here is your residual. And we're squaring the residual and dividing by n minus 2. This is different, right? It used to be n minus 1 if you're doing a sample standard deviation. But since we're doing it for residuals, we're using n minus 2 here. Okay, so just keep that in mind. That's a little different. Remember, n is how many data points you have. So what's your sample size here? All right, so there's our formula. Let's actually go ahead and look at an example. So for the following set of data, make a residual plot to determine if the regression line given by that regression equation is a good model. Find the standard deviation of the residuals and interpret this value. So we're going to make a regression plot real quick. So in this case, we have on the y-axis, we have our residuals. So we need to actually calculate our residuals first. So let's go ahead and do that first. So in order to do that, we need to calculate our y-hat. So we're going to go ahead and actually calculate that. So in order to do the first one, we need to do y-hat equals, we're going to use our equation that they give us. And we're going to plug in x equals 12 first and get that y-hat. So if you did that, you're going to get 18.404. So we have 18.404. And then we're going to repeat that for the other one. So now next we're at x equals 9. And we get 15.269. Next we're at x equals 15. 21.539. And lastly, we're at x equals 20. 26.764. So now we're going to do our residual, so y minus y-hat. So we're simply subtracting these two numbers right here. So that's 15 minus that number. So negative 3.404. Now we're subtracting 18 minus 15.269. 2.731. Negative 0.539, and then the last one, 1.236. Okay, so normally you want to have as many dots as possible in order to, make your regression. You want to have as much data as possible in order to make your regression or your residual plot, but here we want to just do 4 just to give you an idea of how to make the regression or the residual plot. So to make the residual plot, we're going to have some negative, some positive residuals, right? So this is our 0 line, and this is our residual. All right, so for our residuals, we have, we'll do like maybe 4 on top, 4 on the bottom, since our residuals are not very large. Okay, so and then this x-axis is our, y. Normally you would label this, right? So this is our x values here. So we have, for the x values, let's go by 14, 16, 18, 20. So we'll go by 2's here. All right, so for x is equal to 9, we have a residual, or let's do x equals 12, we have a residual of negative 3.404. So that's around here. For x is equal to 9, we have a residual of 2.731. It's around here. For x equals 15, we have a residual of negative 5.39. It's around here. And then for x value of 20, we have a residual of 1.236. So around here. So if you look, that's our residual plot. You know, it's only 4 dots there for 4 data points. It seems there doesn't seem to be a pattern here. So it's randomly scattered. Some are above, some are below. And in fact, it seems like 2 are above, 2 are below. So it could have just easily have been, you know, 1, 3, or whatever. So there, it seems to be kind of random. Again, the more points you have, the more you're able to assess the randomness of the pattern, you know, to determine if there's a pattern. But for now, you know, it's good enough that we can kind of tell that, hey, this is probably going to be a good model. All right, so it seems to be random. So no pattern, as far as we can tell right now. All right, so this means, you know, an appropriate model. All right, so we have a residual plot. Part B, we want to find the standard deviation of the residuals and then interpret this value. So let's do the standard deviation. So the standard deviation is given by, you know, this formula, square root. You want to subtract, you want to do the residuals squared divided by n minus 2. So let's do that real quick. But in order to do that, we need to we need to extend this chart here. So this is negative 3.404. We're going to be doing the squared residuals here. So we're going to be squaring these guys. All right, so if we square the first number, we're going to square negative 3.404. We get 11.59. Next one, we square that, 6.12. 0.29, 1.53. So now we're going to do the sum of this column. Because that will give us our numerator here. So the sum of that column, we need to add those numbers up. And you get 19.53. So that number goes in the numerator. So now we have square root of 19.53 over how many numbers do we have? So we have 4 numbers for x, so n is equal to 4. So we got to do 4 minus 2. 4 minus 2. And that will give us our standard deviation or residuals. And that'll be 3.12. All right. So then if we look at part C, we want to interpret this value. So if we want to interpret that value, well, that just says that, so what that's saying is that 3.12 is the typical distance from the predicted and the actual value. So the typical residual is 3.12. So basically, so what we could say is, we could say here that the y value is typically about a distance of 3.12 from the predicted y value using the least squares regression line. All right, so now we're going to talk about the coefficient of determination. So besides the standard deviation of the residuals, which we calculated earlier, we can also use the coefficient of determination r squared to measure how well the regression line makes predictions. So the coefficient of determination r squared measures the percent reduction in the sum of the squared residuals when using the least squares regression line to make predictions, rather than the mean value of y. In other words, r squared measures the percent of the variability in the response variable that is accounted for by the least squares regression line. So it's a mouthful there. Let's walk through an example so that we can kind of get an understanding of what r squared measures. So suppose we wanted to predict the price of a Ford F-150, but we don't know how many miles it had been driven. We know that the average price is $27,834 from the data, and we know that the standard deviation of the prices is $9,570. We also know that the correlation coefficient is 0.812, so this is a good linear relationship. All right, so suppose we want to predict the price of a Ford F-150, but we don't know how many miles it had been driven. We know that the average price is $27,834. That's from the data that was given. And the standard deviation of the prices is $9,570. The correlation coefficient R equals 0.812. Our best guess here would be the average cost of a Ford F-150, which is $27,834. That's if we had no knowledge of the mileage that was given. However, if you use this average as your guess for the cost of a Ford F-150, not knowing how many miles it had been driven, there's a very good chance that this would not be a very good prediction. And that's because the standard deviation of the prices is high, very large spread. So there's a good chance that, it's plus 10,000 or minus 10,000 because the standard deviation is about $10,000. So there's a good chance that it's, a little over 10,000 or a little under 10,000, less than your guess. So if we knew the mileage, we can use the least squares line to make a better prediction. So how much better are the predictions using the least squares regression rather than using the average price? This is what the r squared, the coefficient of determination, actually tells us. So how do we go about calculating this? So if we look at the graph below, the two graphs, so we have here on the left, we have the average price of a Ford F-150, which we said, was $27,834. Now, if we use the average price as our guess for the price given any number of miles driven, because we don't know what that is, then we were able to calculate the residuals by taking each data point and subtracting it from our average guess, right, which is 27,000. So, for example, this dot, if we take the difference, the residual between that and the 27,000 line, we're going to get a residual for that. If we were to do this for all of these coordinates, subtracting the y minus our y bar, then we're gonna get a bunch of residuals, and notice that these residuals are pretty large. Like some of these residuals are very large between this and our prediction here. So if we were to square those residuals and add them up, we're gonna get this number here. That's a pretty large number if you think about it. There's 3 zeros there, 6 zeros. So 9, so this here is 1,374,000,000 as our sum of squares residuals. It's pretty large. Now, compare that to our regression line. If we were to do a regression line and we were to do the residuals between each data point and our regression line, the residuals are much smaller if you notice, on average, right? So these are not that large. Some of them are quite large, but a lot of them are small. That's because this is a good prediction, right? This is trying to say that this is minimizing the squared residuals. So now, if we were to calculate each of those residuals and square them and then add them, we're going to get a sum of squares of this, which is substantially smaller than the previous. This is 461,300,000, which is way smaller than 1,374,000,000. Big difference here. How much of a difference? Well, that's what the R squared tells us. So the R squared tells us how much of the variability has been reduced when we used a regression line instead. So to find R squared, we need to calculate the percent reduction in the sum of the squared residuals. So SSR stands for sum of squared residuals. So we take the sum of the squared residuals for our Y bar, that's this guy right here, when we use the Y bar to make a prediction, which is the billion number, minus the sum of the squares for the Y hat. Remember that this is our Y hat, and this here was our Y bar. Subtract those, and then we divide it by the original sum of squares of Y bar, and we get 0.66 for our coefficient of determination. So what does that mean? Well, that means that the sum of the squared residuals has been reduced by 66%. If we convert this to a percentage, that's 66%. So the sum of the squared residuals has been reduced by 66% when we go from the Y bar to the Y hat, which is a big difference. This means that 66% of the variability in the price is accounted for by the least squares regression line. That means that least squares regression line reduced all of our variability by 66%. Now, what happened to the other 34%? Well, that other 34%, has not been accounted for by the least squares regression line, which is why we have some of those errors, right? We have a little bit of error. And that remaining 34% can be due to other factors, such as maybe the age, color, condition, or other features of the truck. Now, the easiest way to calculate this R squared, however, besides doing the calculation that we just did, is to simply square the value of the correlation coefficient R. And that's what we do here. So they gave us that the correlation coefficient is 0.821. All we do is simply square it to get 0.66, which is the same result that we had earlier. So this is the easy way, by far the easiest way to calculate R squared, is by taking R, which we know how to calculate now, and square it. All right, so let's look at the following problem. We want to calculate and interpret the R squared, the coefficient of determination. So before, we used the least squares regression to model the relationship between the amount of soda remaining and the tapping time for cans of vigorously shaken soda. The correlation coefficient obtained was 0.922, and this was back in the previous lesson. What is the value of the coefficient of determination? And remember, the coefficient of determination, that just means R squared. So let's find the value of the coefficient of determination. All we got to do is we have to square the 0.922. And that gives us our coefficient of determination. Very simple, rather than having to do all of the calculations that we did earlier. So we get 0.85 for our coefficient of determination. What does that mean? Well, remember, convert that to a percent. This means that 85% of the variability in the amount of soda remaining is accounted for by the least squares regression line. In other words, 85% of the variability has been reduced in going from the Y bar to the Y hat, and going from the average amount to the least squares regression amount. All right. All right, and that is it for the video, guys. And that's it for the lesson. I hope you learned something from this lesson, and I hope that you know that this lesson made sense. And I'll see you in the next one.